Hi everyone, I'm Mike Jacoby from LUCID Vision Labs, and welcome to our presentation, Time-of-Flight Design Tips, tips to boost 3D performance and cut integration time and cost. In this presentation, we'll go over some common challenges associated with time-of-flight cameras, also known as ToF cameras, and some tips to help overcome them. Now, a quick note that a lot of the camera features presented here will be highlighting LUCID's 3D ToF camera, the Helios, featuring Sony's IMX556 depth sense sensor. So if you have a different ToF camera, certain features may or may not apply. LUCID designs and manufactures industrial machine vision cameras, and we were the first to integrate this sensor into an industrial Ethernet camera. Since the camera's launch in 2019, we've seen it successfully deployed in a wide range of applications, including palletization, food inspection, bin inspection, and more. We'll go into more details about what applications it's best suited for in a bit, but right now I want to give a quick high-level overview of how time-of-flight calculates 3D depth data. In general, you need two major components. You need a ToF sensor, and you need a light source that emits pulsed light. The emitted light can be either laser, IR, or visible light, but most current ToF cameras use near IR. 3D depth data is calculated by measuring the time it takes for the emitted light to be reflected from the scene and back to the sensor. Now there are different types of time of flight. There's direct time of flight and indirect time of flight. I won't go into detail about the two, but for the sake of this presentation, we'll be talking about indirect time of flight. So some benefits to using time of flight are no in-field unit calibration required. This means if you buy a ToF camera, you can take it right out of the box, plug it in, and get 3D imaging right away. It suffers from no occlusion and comes in compact sizes. Some additional benefits possible but are more vendor specific are multiple ToF cameras can be combined to increase your depth scene field of view, and ToF can be combined with a regular color camera for color overlay. Please note that these last two benefits are vendor specific and will require some calibration between units for them to properly sync up. Now there have been ToF sensors on the market for some time, but the latest to come out is Sony's IMX556 depth sense sensor. The sensor offers VGA resolution at 30 frames per second, along with excellent 3D imaging performance, thanks to its current assisted photonic demodulator technology, combined with their backside illuminated pixel technology. This results in high quantum efficiency and high demodulation contrast, both of which are needed to help produce high accuracy and precision in a 3D point cloud. For those looking for more in-depth information about how Sony's depth sense sensor works, we have a free tech brief on our website, so be sure to check it out. We're highlighting this sensor because, as mentioned earlier, this is what we use in our Helios 3D ToF camera. We've integrated this sensor into an industrial robust camera that's compact and lightweight. It has a wide ambient operating temperature, has secure M12 and M8 connectors, integrated AR-coated lens, and is paired with high-performance VCSELs which are eye-safe certified. Each unit is also quality tested and pre-calibrated. For those looking for an embedded solution, we also offer the Helios Flex camera module. It has many of the same features as a regular Helios camera, but is smaller and lighter and is designed to take full advantage of NVIDIA's Jetson TX2 embedded platform. Okay, so our first tip is about understanding which applications ToF is best suited for. In this graphic, we are comparing working distance to 3D accuracy. All ToF cameras have a stated working range, as well as accuracy specifications. Our Helios camera is best suited for a working distance range of 0.3 meters up to 6 meters. Also, the accuracy of Sony's depth sense sensor maxes out at around 5 millimeters, so any highly detailed 3D scanning such as optical metrology isn't really what it's designed for. It's best suited for applications such as short-range robotic navigation and obstacle avoidance, and automated material handling such as palletization or bin inspection. So now that we have a better idea on what it's suited for, how can we optimize the application environment to get the most out of our ToF camera? First thing we should look at is lighting. Here we're showing the spectral response curve of the Helios. We're highlighting two specific wavelengths, one at 850 nanometers and 940 nanometers. These two wavelengths are important because depending on if you plan on having an outdoor or indoor application, that will dictate which wavelength of emitted light your ToF camera needs to have. Outdoor ToF cameras have emitted light at 940 nanometer wavelength. This is because there's a natural dip of sunlight at this range. Outdoor ToF cameras will also have a bandpass filter to block out the rest of the sunlight from interfering with the sensor. If it didn't have one, the intensity of the sunlight would easily oversaturate the signal. So, if you need a ToF camera for outdoor use, it's important to choose one that has a bandpass filter and that emits light at 940 nanometers. Looking at indoor applications, here are the typical spectral response curves for common indoor lighting types. You have incandescent, halogen, fluorescent, and LEDs. What you want to do is try to limit as much ambient light at 850 nanometers as possible, as this is the most common wavelength used for emitted light on indoor ToF cameras. Of course, you'll also need to remove as many sources of sunlight as possible for indoor applications. While incandescent and to a lesser extent halogen both emit light at 850 nanometers, it's important to note that Sony's depth sense sensor can cancel out most indoor ambient light, as indoor lighting is at a much lower intensity than sunlight. However, the more ambient light that needs to be canceled out, the lower the dynamic range and higher noise you'll have in a 3D scene. Fluorescent lighting might look good, but it can be troublesome if they have a low flicker refresh rate or in general are just of lower quality. This can cause distortions in your 3D point cloud. Overall, we recommend uniform DC lighting such as high quality LEDs for indoor use. So some people have asked, can you use an outdoor ToF camera for indoor use? Well, yes you can. But if we go back and look at the heliospectral response curve, we'll see that an outdoor ToF camera using 940 nanometer light will be at a disadvantage to that of an indoor ToF camera using 850 nanometers, as it will be only operating at half the sensitivity due to the lower quantum efficiency at 940. Next up is target and camera motion. If you take a deeper look at the anatomy of one depth frame of the Sony sensor, we see that it's actually composed of 4 microframes, each one stepped at 90 degrees. What this shows us is that if the object or camera is moving too fast for the microframes, it's possible we'll get some 3D distortion. In addition, we also have to be aware of the camera's working frame rate. The Helios camera has 2 modes: near mode, with a working range of 1.5 meters or less and operating at 30 frames per second, and far mode, with a working range of 6 meters or less and operating at 15 frames per second. Far mode on the Helios actually runs at 30 frames per second, but we split the frame rate between 2 VCSEL frequencies in order to get better accuracy and precision at farther distances. So here's an example. The middle image shows motion distortion of a moving box captured on the Helios running in far mode. And on the right, an example of the cardboard box moving at an appropriate speed. In general, operating frame rate as well as distance to moving object will dictate max object speed. As a general rule of thumb, we've calculated that an object at 1 meter distance to the Helios running at 30 frames per second, the max speed can be 0.1 meters per second, and at 15 frames per second, half that at 0.05 meters per second. Now let's move on to specular and non-reflective objects. Here we have 2 pairs of PVC piping, a black pair and a white pair. If we look at the corresponding point clouds of the white pipes, we see a nice, clean point cloud. The black piping, however, we're getting a lot of distortion. This is because these pipes have high specular reflective areas reflecting 850 nanometer lighting, which creates these peaks in the point cloud. It also has absorbent non-reflective areas, which creates these voids and empty areas. So how can we deal with these issues? Well, the Helios camera provides 3 major settings you can adjust to get a cleaner point cloud. We can adjust exposure time and gain, increase image accumulation, and adjust confidence threshold. The Helios offers 2 settings for both exposure time and gain. For dark objects or objects at farther distances, you want to set a high exposure time and a high gain. For very reflective objects or objects at closer distances, you want a short exposure time and normal gain. In addition, you can adjust image accumulation, which allows you to stack point cloud data from multiple frames. Here are 3 point clouds of a dark plastic palette. One at 2 stacked images, 8 stacked images, and 30 stacked images. As you can see, the more images we accumulate together, the cleaner the point cloud becomes. However, the downside is that the higher image accumulation, the lower the working frame rate. Finally, we can also adjust the confidence threshold. Each point in a point cloud has a level of reliability in its position based on its temporal variations. Points with less confidence can be filtered out by adjusting this threshold. So sometimes it's enough to adjust one of these settings, but most likely you'll need to adjust all three together to find the right balance. In this next slide, we're going to talk about object multipath. First off, what is multipath? It's when the emitted light reflects onto multiple surfaces before returning to the sensor, as opposed to just reflecting once and then back to the sensor. In this example, we're showing how a loss of detail can come about with concave angles. Here we have 3 cardboard boxes with 2 of them placed together to create a concave angle between them. What's happening is that the emitted light from the helios bounces off one surface, then onto another, and then finally back to the camera. Because of this, the camera has a hard time with that middle corner and a loss of detail occurs. Now, we've put a lot of effort into reducing this type of multipath, but there are some situations where the best you can do is just minimize it by reducing these types of concave angles between objects. And you also want to remove any non-essential specular objects from the scene. Another form of multipath is based on the surface background reflection. On the left are images of a white pipe and a white plastic bottle. These items are placed on a white background, and as you can see, the emitted light is bouncing off the background, then onto the object, and then to the camera. This extra reflection pushes the curved surface and results in a more stretched out looking pipe and a more triangular looking bottle in the point cloud. Now, if we replace the white background with a light-absorbent, non-reflective surface, we see a much better point cloud that's closer to reality. If we compare the pipes, we see that it's not as stretched out as the previous version, and the bottle has become much more circular, less of a triangle. It still has a tiny peak, but overall the surface background multipath in the scene is greatly reduced. So choose a non-reflective background surface to reduce background multipath. Note that I didn't say black background because some black surfaces can be just as reflective as lighter colors. Moving forward, another issue some people encounter is ambiguity or wraparound. In this example, we have some cardboard objects placed at 1.4 meter distance to the helios. The helios is set to near mode, which has a maximum range of 1.5. The objects appear at the very end of the point cloud and everything looks normal. But what if those objects got moved slightly past the maximum range? Say we move it to 1.7 meter distance. What can happen with objects that are just outside the working range but very close to it is that they might wrap around and pop up in front of the scene. In this example, the objects are placed at 1.7 meters but are actually showing up at 0.2 meters at the front of the scene. If we take a closer look, we can see how the wrapped around objects are showing up. How to deal with this? Well, first you want to try and remove any objects outside the camera's working range and field of view that you don't need. You can also change the working range. In this case, you would change the helios from near mode to far mode. But if that's not possible for your application and you're still getting wrapped around objects, the helios offers the ability to fine-tune the depth distance range. Here's a cropped screenshot of our depth range selector in our Arena View software, with the scene being set to show only points starting at 400 millimeters and ending at 3200 millimeter. So any points, including ambiguous points showing up before 400 millimeter, will be filtered out. One last issue we need to be aware of is frequency crosstalk interference. When you have 2 or more ToF cameras with intersecting field of views, and if they're on the same frequency, they can interfere with each other. For example, we have 2 helioses placed right next to each other. This type of interference can result in a sort of pulsating point cloud during real-time streaming. Basically, you'll be getting inconsistent depth results from frame to frame. What you want to do is set each unit on a separate frequency channel, if your camera supports that. We call them communication channels, and the Helios supports up to 5 of them, with each channel's frequency being just slightly different enough to avoid interference. So for example, if you have mobile robotics where their paths might crisscross, or if you're setting up a multiple ToF application, this is something you'll need to do to set for each unit. Here we're demonstrating 3 Helios cameras working in the same space without any interference, and stitching together each one's point cloud to view in real time. Well, that concludes this presentation. Hopefully you found this helpful. If anyone has additional questions or comments, or wants to know more details about these issues, please feel free to contact us. We also invite everyone to check out our online resources on time of flight. We have a tech brief that goes into great detail on how the depth sense sensor works. We also have 2 white papers, one specifically on the topics discussed in this presentation, and another white paper comparing ToF to other 3D technologies. Thanks so much for watching, and I'll see you next time.